Guys, welcome back, and this is the last lecture video on blood identification. I promise, at least from me. You'll have some external videos that you need to watch, but again, from me, this is going to be the last identification test that we are going to talk about throughout this process. All right. So in the previous videos, we talked about a couple of ways to identify blood. One was the presence of phenolphthalein, and we're comfortable with that maybe. So that was the Kastle-Meyer test again. And then the next one was this hemostick and hemotrace that we also talked about. And then finally in the last video that you probably just watched before this one, we talked about UV light. UV light with different filters and different ways that we can make different stains show up on a piece of fabric or a piece of clothing, whether that is a light colored piece of clothing or a dark colored piece of clothing. Now what we want to do is we want to focus on a different reagent-based compound, and this is something called luminol, all right? So luminol is a reagent. It is a powder, and this powder I can dissolve in solution. And typically this solution requires a little bit of peroxide, H2O2, and a little bit of base. And this process will work. There's a reaction that happens here, and this reaction is called chemiluminescence. All right, so chemiluminescence. So what chemiluminescence does is basically takes a compound and you put energy into this compound. And electrons, like you've learned about in chemistry 151 and 152, begin to jump orbits. And they'll jump orbits or energy levels, and then they will eventually settle back down. All right? When they settle back down, they have to give that energy back off in some form or some fashion. The law of conservation of energy says what you put in, you have to get out. So if we're putting energy into the system and electrons are jumping, then electrons are going to settle back down when they go through their sugar crash, and they will release this energy as they settle back down to ground state. Well, sometimes compounds like luminol, when they begin to settle back down, this energy that is given off is simply in the form of light. And we call this chemiluminescence, right? This is a chemistry reaction kind of that's happening. It is changing the luminol, and the luminol structure is somewhat reverting back on itself, and these electrons are settling back down. When it does, they give that energy back off, and when they do, they give it off in terms of light energy. We can actually see this light that is being given off. So the way that I want you to kind of keep this in mind, imagine a completely darkened room, all right? So this completely darkened room is filled with luminol. And luminol right now is not doing anything at all. There's no reaction. Nothing is promoting this reaction to happen. We typically need a catalyst for this to work out really, really well. And then sooner or later, what's going to happen is that if we give it a catalyst, then boop, we start to see light energy that shines from this compound or from this molecule. And we see that, especially if it is in a darkened area. So the reason that I'm telling you this is the luminol test will typically require a very dark environment. Okay. Now, it doesn't need to be completely dark. You're going to be able to see the luminol kind of glow and fluoresce, even if there's a little bit of light into the room. But in order to really see these low-key stains, a completely dark room or a dark environment is going to be pretty important. That is also another reason that these tests are typically done at night at crime scenes and stuff, because luminol is portable. It is a reagent. It can easily be taken out to a crime scene and sprayed or misted onto an area in order for this chemiluminescence to pop up. So how does this reaction work? Well, once again, like we started with, we are going to focus on the heme group one more time. And heme is going to include iron. So if iron is present, iron will actually oxidize the luminol, and it breaks a bond and it oxidizes the molecule. And then as the molecule tries to revert back on itself, or as it gives up this energy, it will give off this energy in terms of light energy that we can see. Luminol is great for traces of blood, and it's also great if someone has tried to clean the crime scene. Luminol is so particular and selective that it can pick up even the very slight trace of blood from the heme or the iron that might be present. Meaning that if I was on a crime scene and I wanted to clean up my act before I left to make sure that I can get rid of DNA and everything else that might associate me to that crime, and let's say that I bring out a bottle of bleach or something and I try to clean that crime scene up, and I try to get as much blood as I can cleaned off of the floors, off the walls, off the knives or guns or whatever I've decided to handle, this luminol will be able to pick up that presence even after it is cleaned. The problem is that luminol doesn't just react with blood. It reacts with anything that can oxidize it. And the issue here is that bleach is actually one of those things that can make luminol oxidize. So when someone decides to clean up a crime scene with bleach, they are spreading this oxidizer all over the other oxidizer that was there, and the luminol will be able to pick that up. Everything will glow kind of bluish in color with luminol. So if I pull up this slide, this is kind of what you're seeing over on the right-hand side of the screen. This is luminol that has been sprayed onto a sink, and what you're seeing is basically the remnants of what had been left there beforehand. Not only bleach will cause the luminol to react this way, but there's some other things like various metals, because it is an oxidizer, and this is iron-based again, right? Paints, cleaning products including bleach, and plant materials. So anything that carries iron or copper, that is going to be a dead giveaway for luminol. That's what it needs in order to give us this very blue distinctive color on a crime scene or an object. The problem here is that luminol, you've got to be very careful. Here at the bottom, I've said it can destroy other evidence at a crime scene, and people can get careless with luminol. So luminol, you are going to have to spray, right? We have to spray this onto the sample. And as you're spraying it, you run the chance of diluting that stain, and that stain can actually spread and do other things, and maybe that's not what you want. So if you get carried away, you can actually use too much luminol, and then before you know it, the entire sample area doesn't make any sense anymore. So luminol is very good in very low amounts, all right? You don't want to apply a lot of this. So because of that, we often say that you will mist the area with luminol, but you will not saturate it with luminol. Another problem with luminol here is that this reaction that you're seeing here just lasts for a handful of seconds, all right? So if you're not careful, you will spray this luminol, and if you're not paying attention, the blue color will show up, and then the blue color is going to immediately start to fade on you. And if you cannot catch that color change, then you're going to spray and spray and spray and spray, or you might miss stains or samples that could be present at the crime scene, and you don't want that either. All right, so up here at the top is the structure of luminol. We see this ring structure that is like a benzene ring with an NH2 group on it, and that is called an amine for those of you who are not inorganic. And then here we see another ring structure beside of it, but this is a nitrogenous ring. Nitrogenous means there is nitrogen in the ring other than just carbon all the way around. So we see a nitrogen here in the top corner and a nitrogen here in the bottom corner. These double bonded O's, one on top and one points to the bottom. It's a pretty symmetrical molecule, right? So this area here, that is classified as a carbonyl bond, C-A-R-B-O-N-Y-L. So that is a carbonyl. And when a carbonyl is attached to a nitrogen, like it is here in the ring, This really turns into an amide now with an IDE ending. It's a different type of functional group than just a carbonyl or just an amine. When that combo comes together like that, we refer to it as a whole group of its own, and that is called an amide. So we have one amide group that's here and one amide group that's there. So you're probably looking at this name, and if you're inorganic, you probably have looked at this ending here and said, well, now wait a minute. In organic, we learned that if anything ends in OL, then it's probably an alcohol. But nowhere on this molecule do I see an alcohol, right? You've just told me that we have an amine group and that we have an amide group and these carbonyls, if you want to look at those separately, but nowhere did you say that we have an alcohol. So why is it called luminol? Well, sometimes these kinds of names happen for common reasons. They don't really think about it that much, and they can term this luminol with an OL ending, but it not have an alcohol group at all. However, this kind of leads us into the area of what could be, all right? So if we look down here in this flow chart, you're going to see luminol structure right here. And if we have peroxide and some type of catalyst, and that catalyst could be copper or it could be iron, then this NH to NH bond that's right here, that NH to NH bond is going to cleave, right? And if you take a look at the NH and NH, what we actually end up with here on the ends are oxygens. And these oxygens could, if under the right circumstance, end up with OHs there, right? They're just free O's right now. And that O, it's probably so tiny you can't really see it. But that O, the way that they've written it, is an O with a minus. So if this is in somewhat of an acidic condition or an acidic environment, this O minus will eventually turn into an OH, and there is the presence of your alcohol groups, which is kind of related to the word luminol in the very end. But this is the reaction that's going on. So the NH to NH bond breaks, and we see the removal of the amide. The NH group goes away. And on its place comes this oxygen, and it's not an amide anymore. This is something completely different, almost kind of like an ester group, right? And then, if under the right circumstances, we can get this H slapped onto the O's in the very end. And this is what gives us the light energy. All right, so there you go. Up here at the top, you're going to see other things that react with luminol, not just blood, but blood is kind of the number one thing that we're looking for. Bleach that maybe can be used to clean the crime scene up will also show a positive blue color when sprayed with luminol. Feces, aka poop, and urine. So I would hate, again, to spray luminol into people's bathrooms, maybe in this own classroom. I would hate to go to your bathroom and spray luminol in because it would be a horrid sight and I would probably never step foot in it again. But feces and urine will also show a positive charge. And finally, over here at the very end, horseradish. Horseradish actually has an enzyme on the inside of it that will trigger a blood sample to show up. So in other words, if we wanted to be sneaky in the lab and if we wanted to maybe show you the presence of luminol on a piece of fabric or solid surface, we could go buy horseradish in the grocery store and we could smear it all on that piece of fabric and say, is there a blood stain? And with your naked eye, you would say no. But with something like luminol, this would show up as a positive blue glow. All right. So once again, we have a reagent-based reaction that does have contamination or false positive reads with it. We just have to be careful, and that's the purpose of the forensics lab. Yes, this showed a positive test, but can you confirm if blood is actually there or not? Luminol is not a complete confirmation test, all right? Hardly any of these are. We've only talked really about one that is positive for a blood sample. Finally, one more thing here at the very end is this thing called Luso Crystal Violet. And you see the structure there into the center of your screen. Once again, they are more benzene rings, and off of each benzene ring, we see this nitrogen-containing group that has a methyl here and a methyl group there. This is a very symmetrical molecule all the way around, and this is what we regard as LCV, or luso-crystal violet. It is a way that we can apply another reagent or a compound onto a blood sample, and it makes it more visible, so we can actually see it with the naked eye. Luso-crystal violet, as you can imagine, a violet color will probably show up, and it does. So over here to the side, you actually see a fingerprint that has been marked with luso-crystal violet. We can photograph this, we can analyze this, we can bring this into the laboratory, we can take it to our courtroom for evidence, but it's so bright and it's so distinctive that any normal camera will be able to work with this thing. So once again, you see a YouTube link that's there. This YouTube link will be embedded into Blackboard in the external folder, so that way you can watch these external folders before you attempt the lecture assignment quiz. All right, so that's really all that I need to say about blood identification. A handful of different ways in order for us to look at a piece of evidence or look at a crime scene and to determine if something red is actually blood or not. In addition to that, maybe there's things there that we can't see with our naked eye, and these reagents will actually allow us to see those much, much better versus, bringing it into the laboratory and saying, here you go. Does this look red? Where's the stain? Are there any secrets that this piece of article of clothing or that this piece of evidence is holding back from you that we need to figure out? And that's part of a forensics laboratory technician's job. All right. Okay, so good luck on the pre-lab, or not the pre-lab, but good luck on the lecture assignment. Again, if you've got questions, let me know. Send me a quick email. If something doesn't really necessarily make sense, maybe I can help clarify that up. But good luck to you. I don't think that these are necessarily too difficult. No really chemistry or reactions that we're talking about that much. We're just introducing you to different reagents that can do this job for us. And it gives me a chance to talk about organic chemistry too. And I know that you're happy with that, right?